In this video I want to try and introduce us to the inverse trigonometric functions, which are the functions that are the inverse operations, if you like, of sine and cos and tan. So we're aware of inverses of other functions in the same way as multiply and divide are inverse operations and add or subtract are inverse operations. We sometimes think of them as the things that sort of undo an operation. So here's another one. In the same way as y equals x squared and y equals plus or minus the square root of x are inverse functions or inverse relations if we take the whole of the plus and minus square root of x. So they are things that sort of do the opposite to each other. They undo, one sort of undoes the effects of the other. In the same way as that's true, so for sine x, cos x and tan x, we have inverse functions which are y equals inverse sine x, inverse cos x and inverse tan x. So that's how we sort of describe those. Inverse sine, inverse cos, inverse tan is how we say those. And sometimes they're given the names arc sine, arc cos and arc tan. So if you've ever seen those around, that's just an alternative way of saying inverse sine. And that might be useful sometimes to, emphasize the fact, apart from anything else, that we don't mean sine x to the power of -1. So it's not a power, it's just a way of describing an inverse function. Well, one of the characteristics of all inverse functions or relations is that when we graph them, they will be the reflection of each other in the line y equals x. So if you could picture the graph of y equals x squared, which is sort of a parabola that looks like this, y equals plus or minus root x is a parabola on its side, like this here. And those are in fact the reflection of each other in the line y equals x. So let's take that idea and apply it to the graphs of sine and cos and tan, just to try and investigate a little bit what these curves might look like, these inverse functions. Well, there's the graph y equals sine x, and we know it's sort of a continuous function, a repetitive periodic function that goes on forever. So if we were just to try and draw what that would look like if we reflected it in the line y equals x, this is what it would look like. So there it is, and I've graphed that, as you can see, by using x equals sine y. Now one of the issues we've got with that, and I don't know whether you pick this up straight away, is that that is not a function. It fails the vertical line test. And so if we're going to define inverse sine of x as a function, what we need to do is, instead of just defining y equals sine x over a sort of unlimited domain, we're actually going to limit it to just the domain negative pi on 2 to pi on 2. So if we just considered the inverse or the reflection of that curve in the line y equals x, well, we would get y equals inverse sine x. Let me just remove the original one there. So that is the graph of y equals inverse sine x. And you'll notice it's not sort of, bending around back on itself here or bending around back on itself here. And so that passes the vertical line test. That is a function. What I want you to notice reasonably quickly here about this is that, and this is true of all functions and their inverses, so if we look at the domain of y equals sine x when we restrict it to negative pi on 2 to pi on 2, what you should notice is that that becomes the range of the inverse. So this is negative pi on 2 here, so what's that, about half of 3.14, and likewise up to the to positive pi on 2 there. So the domain of the original function has become the range of the inverse, and likewise the range of the original function, which was -1 to +1, so -1 up to +1 for the original function, that is now the domain of its inverse. So this is going from -1 up to +1 there. Alright, so that green curve there is the graph of y equals inverse sine x. Now then we could think about transformations of that by, adding an a value at the front or a b value in here, or maybe translations with a c and a d value where we shift it horizontally or vertically or that kind of thing. But this is the basic function y equals inverse sine x or y equals arc sine x. Alright, let me go fairly quickly then through cos and tan. So here's y equals cos x, but in order to get its inverse, I've limited it just to half a period starting from x equals 0 and going up to x equals pi. Now I'm not sure if you can picture what that would look like if we reflected it in the line y equals x. Maybe in fact if I was to draw the line y equals x in there, that might help a little bit. So there's the line y equals x, and we're going to reflect the black curve in that, and that's what it would look like once we reflect it in the line y equals x. Let me remove the line y equals x there. So here we had a domain of 0 up to pi. The inverse function has a range from 0 up to pi. There it is, 3.14. This one had a range again from -1 to 1. We know that's true for sine and for cos. So that's become the domain from -1 to 1 of the inverse function. And finally, if we consider tan, well, tan keeps repeating itself over a period of pi, doesn't it? But I've just taken one period of tan here between the asymptote at -pi on 2 and +pi on 2. And so that's what it looks like over that. So if we reflected it in the line y equals x, well, these bits here that are sort of above that line are going to be down below that line. It's still going to pass through this same point and then curve back this way here. Let's have a look at inverse tan. There it is. So removing the line y equals x, let's remove the original function. There's inverse tan of x. Notice that in the same way as the original function had a domain from -pi on 2 to pi on 2 not inclusive because they were asymptotes. So this here is approaching an asymptote of y equals -pi on 2, and this side up here is approaching y equals +pi on 2 as an asymptote. So the range is from -pi on 2 to +pi on 2 inclusive. The domain, well, the range of tan x was unlimited. It was going to -infinity and +infinity in those directions. So this one here, the domain is any real number. Alright, that's a pretty quick introduction. Let's just go back and summarize that fairly quickly. And you can get these ones down if you like. So there's y equals inverse sine x, and I've noted its domain and its range. And those ones are inclusive, so they've got the square brackets. For y equals inverse cos x, there's the graph of it between -1 and 1. And the graph of y equals inverse tan x, which has a domain of all real numbers, but its range is between -pi on 2 and pi on 2, not inclusive. As I said before, we can do transformations of all of these, which could alter the domain and the range if we shift them around or dilate them, but those are the basic inverse trig functions.